session. I'm Roberto Corrao, and I'm going to present this work, Nonlinear fixed points and stationarity economic application, which is a joint work with Simone Cerreia-Vioglio from Bocconi University and Giacomo Lanzani, who is a postdoc at Harvard, joining Berkeley next year. And let me introduce this work as like part of a bigger and broader research agenda that we have now studied for many years about interactions in networks, economic interaction in networks, so general equilibrium models or game theoretic models, in which we relax one of the main assumptions that has been done in the recent literature, which is linearity. And therefore, we face the technical challenge of analyzing fixed points that are by nature and by assumption nonlinear. And working on other papers, we found some structure, some mathematical structure that then we decided to put all together in this more technical paper that delivers some theorems about nonlinear fixed points. But let me introduce first briefly why we care about fixed points. Well, in economics and also in CS, fixed points are pervasive, fixed point equations, both of course in general equilibrium. Usually general equilibrium is a fixed point in the space of prices, or in game theory, usually Nash equilibria or basically any kind of equilibrium that you can think about is a fixed point in the space of actions or beliefs, or even in dynamic games, you can also define, it's useful to define a fixed point in the space of continuation value. So for example, in a single decision problem, you have the Bellman equation as we've seen, or in zero-sum game, you have the Shapley equation that is going to characterize the equilibrium continuation value. So in economics, fixed points are important. You can sometimes assume, make assumptions that are going to imply that the fixed point is linear. So for example, you can consider network games or network models in which the best response of agents is linear, for example, because they minimize a quadratic loss function, or in the case of general equilibrium, if the production function is Cobb-Douglas, the main initial assumption, then the fixed point equation is going to be nonlinear. However, more often than not, as soon as you add more realism to the model, or in the case of the Bellman equation or the Shapley equation, you just consider one or two maximizer, then the fixed points becomes nonlinear. And that's why it would be important to understand what kind of results that we know from the literature in linear fixed points can be translated in the case of nonlinearities. But let me refresh your memory by saying, what do we know about the class of fixed points that I'm going to consider in the linear case? So this is some mathematical results that are probably 100 years old. Consider n nodes, so for example, n agents that are connected through a stochastic matrix. Remember, a stochastic matrix is an n by n matrix whose rows are all positive and sum to 1. And the fixed point that I want to consider is this one, in which I'm going to combine with a weight beta, which is the key parameter that I'm going to index the fixed point to. Exogenously given vector of x's, this can be the exogenous states of the world or the exogenous opinions of the n agents, with the endogenous variable, which is x beta, which is the fixed point that I'm going to solve with. The only thing is that the endogenous variable is entering this equation in a linear fashion. So basically, you take, for example, this x beta as the vector of actions of all the other agents, and you have that the equilibrium is a convex linear combination of the actions of the other agents, because you like to match your action to an average of the actions of the other agents, but you also give some weight to an exogenous action, your preferred opinion, or your current location to which you don't want to go too far away. And this is the case of the linear fixed point. And for example, this would be an equilibrium in a model in which we try to match each other action when the loss function is quadratic. But what happens as soon as we give up this quadratic assumption of the loss function, that this fixed point, and in particular that operator W, will become from linear to nonlinear. What do we know about the linear case? Well, we actually can solve, this is a very famous formula that you have seen so many times, I'm sure, for explicitly for the fixed point, which is going to be a function of the exogenous vector of states, but of course of all the iterates of this linear operator. And in particular, a surprising result is that if this matrix of connection is strongly connected, or in the theory of Markov chains is irreducible, so it has a single stationary distribution, or you can call it left Perron Frobenius eigenvector, then the limit as beta goes to 1 of this fixed point, which is the key limit that I'm going to focus on for this presentation is constant across all dimensions. So this vector of fixed points is converging to a single number, and in particular is going to be equal to the vector of exogenous states times this LPF, so this eigenvector centrality of the matrix. And in particular, we also know that the rate of convergence is. So what do we know in the linear case? We know that this limit as beta goes to 1 exists, and in particular, you can interpret this limit as the importance of the actions of the other agents is dwarfing the importance of the exogenous state. Or in the case of Markov chains, this limit, as we have seen in the case of the Bellman equation, means that the importance of tomorrow's payoff, so the patience of the agents, is dwarfing the importance of today's payoff, so the impatience of the agents. This limit exists. You can find a formula for the limit fixed point that is a simple formula involving the eigenvector centrality of the matrix, and the rate of convergence is linear. In this paper, we basically try to generalize all these three results to a class of nonlinear operators and show in what sense these results are robust, also in the case of nonlinear fixed points. Why should we care about nonlinear? I try to argue that we should, but let me be a little bit more specific. For example, in models of networks, like in production networks or in games of networks, as soon as you have a payoff function, as I was saying, that is not quadratic, then the best response would be nonlinear. But even if you want to see, even if you believe that the right loss function is quadratic, but you allow for endogenous networks, so meaning that these agents or these firms not only are choosing the actions or the inputs, but also the connection with other firms and players, then the fixed point equation becomes inherently nonlinear. And in dynamic programming, nonlinearity is assumed from the beginning because both the Bellman and the Shapley equation, in the case of zero-sum game, are nonlinear. So for all these reasons, the results that we have for the linear case are not enough to study the limit case as beta goes to 1. And the main technical contribution is that we're going to address this nonlinear fixed point equation in the limit through differential techniques. In particular, for today, we're going just to see the concave case, so the subdifferential. The super differential is going to be enough. In the paper, we go beyond the case of concave operators and we use the Clark differential, which is a standard technique in decision theory. So we import some techniques from the decision theory, in particular ambiguity, to the study of nonlinear fixed points. But let me be more precise and introduce some mathematical notation. So I'm going to denote with literally just a unit vector in Rn, and we are going to consider a class of nonlinear operators from Rn to Rn. These are nonlinear, but they have some intuitive and useful properties. The first one is normalization. If the input is a constant vector where all the entries are equal to k, then the output of this operator is going to be constant as well. So all the constant vectors are fixed points of t. This vector is monotone. Eiger inputs are going to imply Eiger outputs of this operator. And finally, we have a grain of additivity. If starting from an arbitrary vector, you add a constant vector, then t is additive for this particular operation. So that's the only grain of linearity, or more precisely, additivity that we are going to retain. And you can interpret each row of this vector as a generalized average. Why? Because the output given a vector x is going always to be internal between the maximum and the minimum input that you give. So in a broader sense, these are nonlinear averages. For example, the quasi-arithmetic mean in which you adjust the entries with monotone functions is going to be an example. And what are the fixed points? Well, the fixed point is going to be exactly equal to the one that we saw at the beginning, but we are going to replace W, which is a matrix and linear operator, with this nonlinear operator. But the interpretation is exactly the same. The fixed point depends on an external vector x, on the parameter b that establishes how much the external vector is important. And in particular, we want to analyze the limit case where the importance of x is vanishing and only the endogenous variable are relevant for the fixed point. Given the assumptions that I was making on t is one Lipschitz continuous, which implies that it's almost everywhere differentiable. And this allows us to kind of replicate the idea of network that we have in the linear case. In the linear case, we have a matrix. We can immediately define a graph by just assigning 1 to every entry that is strictly positive. We can replicate through this grain of smoothness, this idea, and defining a graph across the nodes, the end nodes of this system, by assigning 1 in this graph, if and only if the derivative in almost every point, remember this operator is almost everywhere differentiable, is bounded away from 0. So you can find an epsilon that is going to bound from below the derivative everywhere. In other words, I'm going to say that J strongly influences I, if and only if, no matter what is the current vector of external states, the derivative is strictly positive and bounded away from 0. Okay? And I'm going to say that T, this nonlinear operator, is regular if and only if this graph that we just defined is strongly connected, which means irreducible. You can reach any node from any other node in a finite amount of time. So this is a key definition, so let me pause for a few seconds and be sure that everyone is on board. Okay. The first result is for a particular case, the easy case, as we call with Giacomo and Simone, which is the continuously differentiable case. So let me assume that T, on top of the 3 properties that I was considering before, is continuously differentiable. We actually just need continuous differentiability at 0 or at any constant. Given the monotonicity and translation invariance properties, this implies that the Jacobian of this operator is itself a stochastic matrix. So the rows of these Jacobians are positive and need to sum to 1. Now, what is the theorem? Let T be continuously differentiable and regular. Remember, regularity means that this network is strongly connected. Then, not only we have convergence, so this is the first extension of the linear result. So we can prove that entry by entry, this fixed point is converging somewhere as beta is going to 1. Second, we still have the property, thanks to this strong connectedness, that the convergence point is a constant vector, so each entry is converging to the same constant. And also the formula for the limit fixed point, so we have an analytical formula despite the nonlinearity, is explicitly given by what? Well, by the still unique left Perron-Frobenius eigenvector of which matrix? Well, we have several matrices because we have several Jacobians, 1 for each point in principle. But what we show is that everything that is needed is the Jacobian at 0. 0 here could be any constant vector because given translation invariance, the Jacobian with any constant vector has to be the same. So here 0 is just for simplicity, but I could have written down any k, any constant vector. So everything that you need is to compute the Jacobian at one of the fixed points, and you have that the expression for the limit fixed point is not only explicit, but is linear. In other words, starting from a very complicated nonlinear fixed point equation, when you consider the limit for vanishing the vanishing importance of x, you are back to a linear equation, and the eigenvector centrality of the Jacobian at the fixed point is everything that we have. Now, differentiability is a good assumption to begin with because some of the applications that I was mentioning are also naturally differentiable. For example, in model of production networks, as soon as you depart from the Cobb-Douglas production function, but you retain a smooth production function like in Bakai and Fari, you still have differentiability of this operator and in several other applications. However, there is an important application in which also differentiability fails, which is exactly dynamic programming. In dynamic programming or in zero-sum stochastic games, not only you don't have linearity, but you don't even have differentiability to begin with. The Bellman operator, usually it's non-differentiable given that you can have keys. So we actually want to derive a more general result that goes even beyond differentiability. In the paper, we derive this general result here. For today, for simplicity, I'm going to focus only on the non-differentiable but concave case. So I give up differentiability, but I add an additional assumption, which is that T is concave. Now, I cannot define anymore the Jacobian at every point. What I can define, borrowing from convex analysis, is just the super differential of this operator, which is just the set of linear operators that dominate the nonlinear, the concave nonlinear operator. And of course, this set is non-empty exactly because T is concave. Now, each of these linear operators, given the assumption, still must be a stochastic metric. So basically, given this nonlinear operator, you have a bunch of networks that are representing the local derivatives of this operator in each point. Given that you have this set of matrices, and if you assume that T is also regular, you obtain that each of these matrices is strongly connected. So the graph that you can derive from each of these matrices allows you to compute a single stationary distribution, a single left Perron-Frobenius eigenvector, which means that starting from T, I can derive all the possible left Perron-Frobenius eigenvector associated to all the possible super differentials of this operator. And it turns out that even in this non-smooth but concave case, everything that you need to care about in the limit fixed point are just these eigenvector centralities derived by just computing each stationary distribution of all the super differential matrices. And indeed, let T be concave and regular. Again, not only we show that convergence holds, so these fixed points are going somewhere, not only we also show that this fixed point is constant across all the entries, so also this property is robust, but we derive a formula, an explicit formula for the limit fixed point. But now, and this is perhaps the most surprising result that we have in this paper, linearity is lost. So while in the nonlinear but differentiable case, this limit can be exactly characterized by a linear function, here the presence of multiple derivatives remains in this limit, is not killed, and still you have a nonlinear expression for the fixed point. What I want to stress though is that even if this expression for the fixed point is still nonlinear, you have obtained another grain of linearity. Indeed, this operator must be positive homogeneous. So in other words, computing this limit of fixed points is linearizing in a way or another the original nonlinear operator. Indeed, in some applications, especially the general equilibrium and the general equilibrium ones, we want to interpret this result as an alternative to linearizing the nonlinear system of equations that usually macromodel. Now, I don't think I have time to go over the macro application, but I see more CS people than economics, so I think that you don't really care about the macro application. And let me just conclude and leave some space to questions. So what we did, we started from a standard fixed point equation that is pervasive in games, general equilibrium models, and dynamic programming. We argued that the linear case is not enough, and in several cases you need to be able to solve the nonlinear case. We understood what were the results that we knew 100 years ago in the linear case, and we derived in the differentiable and concave, and in the paper for some general class, the equivalent results. So convergence to a constant, an explicit expression for the limit, and the rate of convergence. And we showed that these in the paper, not today, but is very useful in games on networks or in a general equilibrium model with potential networks to actually explicitly compute the equilibrium prices or the equilibrium actions. And given in the paper, we also derive a rate of convergence for this fixed point. Even if you are not interested by itself to the limit, to the expression in the limit, you can use this limit plus the rate of convergence to provide an approximation for the fixed point when beta is away from 1. And that's what we do in the paper. Finally, given that in the first paper of this session we talked about zero-sum stochastic games, we have also an application to zero-sum stochastic game in which, thanks to our result, we can prove that the asymptotic value of games with arbitrary actions, but finally many states, have an asymptotic value, which means that the value of the discounted game and the value of the undiscounted game, as you take the limit for the discount factor to 1 or the limit for the number of periods to infinity, converge and coincide, which is a fundamental result in the theory of zero-sum stochastic games that dates back to Mertens and Kohlberg, and we extend it to the case of compact action space. So I think I might be over time, so let me stop here.